how do you write a half-open interval as a countable union of closed intervals? How to do that? I think I would, well, certainly I'm going to put a B over there, right? That's a slam dunk. What if I did this? I better make that, let's see. Let's think this through. There's A, there's B. What I want to do is have closed sets that just keep marching over to A but never quite get there. So I guess I better have a plus here, right? True? I sneak up on A from the right, but I never get there. I never get there because 1 over I is always a slight positive amount. If you say, oh no, you didn't get to some number that's arbitrarily close to A and above, I'll say, oh yes I did, just make I small enough, I'll get it. So look at this. It's a countable union. Remember, countable unions are in the sigma algebra. So half-open intervals are in the sigma algebra. With half-open either way and closed, right? The union, how would you get, well, you can see how to get a closed interval. It's a complement of an open set. You take the open sets outside the closed interval you want, they're all in the sigma algebra, so the closed one is as well. That's important to remember. Open, closed, and half-open intervals are in the sigma algebra, which means they have lengths. In fact, AB, and AB all have length B minus A. Right? Okay. So, all right, we got all that worked out. Now, here's Lebesgue's wonderful idea. This one. Bear with me. I'm slow. The myelin is flaking off as I speak. Right. Okay. So here's the wonderful idea. Suppose I have a function tooling along here, and I would like to integrate from A to B. Tell you what, let me do a more provocative picture. That doesn't sound good. Okay, there's the function tooling. All right? Now, I insist in advance that the function is bounded. So I can capture it. The range of this function is going to be, say, let's be between here, right? All right. I'm going to partition, not the x-axis, but I'm going to partition the y-axis. Okay? And here's a typical subinterval in the y direction, which I'll extend outwards. And I will find the corresponding set of x's that would be the pre-image of that interval. And it would be those two pieces there, right? This is just a particular one here, and I get these two down here. Okay? Now, these subintervals unlike the Riemann case, I'm going to chop the top off. So it's closed at the lower value, open at the top. Closed at the lower, open at the top. That's what you want, right? Now they're disjoint. In the Riemann case, and the Stieltjes case, and the Darboux case, they overlap with the partition points. Here, these half-open intervals are disjoint. Okay. This is a measurable function. So that means that the pre-image of a half-open interval here is a measurable set. In other words, I am guaranteed by the measurability of the function that the pre-image set has a net length. Okay? The ordinary Lebesgue measure here is lambda. So we'll say that lambda is that length where lambda of any of these is b minus a. Okay? We may choose later to have a more general measure, but for the moment we're just in a very basic case. This is a function from the reals to the reals, and the measure that we're using is ordinary Lebesgue measure, which corresponds to the length of the number. So what I do is, since I've partitioned this, let's see, alpha is y0, and I have y1, blah, 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 up to yn, which is beta, okay? So the range of the function is contained in the interval alpha beta. And I form a sum. I will take a typical element. I'll take a y sub k. So he's sitting in here somewhere. Let's suppose that this particular value here is y sub k, and that's the beginning of the kth. That's the beginning of the kth subinterval on the y-axis. Okay, so that's y sub k. If I take y sub k and I multiply him by the measure of the pre-image of the subinterval. So it's the pre-image of the interval y k minus 1 to k. Maybe I screwed up the indices here. Okay? So this is the contribution to the integral where the height of the function is between here and here, right? Between y sub k minus 1 and y sub k. Y sub k minus 1, since we are chopping off the tops of these things, y sub k is the start. Sorry, y sub k minus 1 is the start of the kth interval, but it's an interval that's not in it, right? Y sub k is in it. Y sub k minus 1 is not. But it is the kth subinterval on the y side, right? So that's a contribution to the area where I go across and come down. So, you know, if I take y sub k, basically this is the rectangle that I'm adding, and I'm also catching this one here, right?
How are you catching it?
How am I doing what?
How are you catching both of those rectangles?
Well, wherever the function has value between y sub k minus 1 and y sub k, I say, go find me the pre-image. In other words, where on the x-axis is the function doing it? I take the total length on the x-axis where it's doing that and multiply by yk.
Oh, so you would just be adding those lengths?
Yes, sir. I would. In principle, I can get a bazillion of these little slivers here. They're all different sizes. I partition this way, find the total lengths this way, and add those rectangles in. So that's the increment of area due to the function ever passing through the subinterval y sub k minus 1 to y sub k. Okay?